section 7.1, this should be a review of exponential equations from us, because a lot of us have done this in Foundations 30. So remember, an exponential equation is one where the x is in the power. Okay, so this has x as the power. Okay, so the question says, graph each exponential function, then identify the following: domain, range, x-intercept, y-intercept, graph, whether it's increasing or decreasing, and the horizontal asymptote. Okay, so if we just remember our key ideas from exponential equations, if this number in front is a whole number, so greater than 1, then it's increasing. And if it's anywhere like a fraction, so anywhere between 0 and 1, then it's decreasing. Okay. So if we were going to look at what this graph would look like, we remember, so this one would be an increasing function, and increasing ones don't cross the y-axis, and they cross at 1 and 0. Okay, so the point is 0 over 1 up. And what else can we talk about? So our x-intercept, we don't have any. There would be no x-intercepts. And the y-intercept would be at 1. That's a 1. Y-intercept of 1. The domain, so if you look, it just keeps going and going, so it would be all real numbers. And the range would be y has to be greater than or equal to 0, because it never crosses that y-intercept. So the next part says whether the graph, we have its increasing, decreasing, the equation of the horizontal asymptote. So we said that it's not going to cross this y-axis. So y equals 0 is the equation of the horizontal asymptote. Okay, so now for this question, it's at a half, so we know it's decreasing. Oh, well, 1 second here. I think I drew my picture as decreasing, didn't I? This one. Sorry. Should look like that. It's increasing from quadrant 2 to quadrant 1, crossing at 1. Okay, this one will be decreasing, and it'll be crossing at 0 and 1. Okay. And so basically there's still no x-intercept. The y-intercept is going to be 1. Domain is xdr. Range has to be greater than 0. And the equation of the horizontal asymptote would still be y equals 0. So nothing really changes besides that this one is an increasing function and this one is a decreasing function. Looking at example 2 on page 338, it says what function of the form y equals cx can be used to describe the graph shown. So basically we want to see what the equation is for this graph. So if we put the points that we have, so we have when x is minus 2, y is 16, minus 1 and 4, 0 and 1, gives us an idea of what's happening to the y's. So is this one going to be a whole number or a fractional number? Is it increasing or is it decreasing? Okay, so this picture shows that it's decreasing, and if you look at these numbers, it goes from 16 to 4, 4 to 1. It's 16 divided by 4 is 4, 4 divided by 4 is 1. So it seems to be a factor of 4. So we can put our c as 1/4, and this becomes our equation. Example 3 is kind of like a physics question. It's talking about exponential functions and with growth and decay. So exponential growth is an increasing pattern of values that can be modeled by the function, so it's when the pattern increases. Exponential decay is a decreasing pattern of values that can be modeled by a function. So decay is when it's decreasing, and exponential growth is when it's increasing. And we use the term half-life is length of time for an unstable element to spontaneously decay to 1/2 its original mass. Okay, so this question says we have a radioactive sample of radium Ra-225 has a half-life of 15 days. The mass m in grams of Ra-225 remaining over time t in 15-day intervals can be modeled using the exponential graph shown. What is the initial mass of the Ra-225 in the sample? What value does the mass of Ra-225 remaining approach as time passes? Okay, so what is the initial mass? So if you look, the picture starts at 1.0. So that means, and that's in grams. So the initial mass would be 1.0 grams. And what does it approach over time? Well, it slowly approaches 0. It's not going to get there, but it's going to slowly approach it. What are the domain and range of this function? So the domain looks like it doesn't go into the negative. You can't have negative amount of time. So x has to be greater than or equal to 0. And the range would have to be y has to be greater than or equal to, not equal to 0, greater than 0. Okay, the next part says, oh, and we need to remember that it stops at 1. So we should probably write this instead of y is greater than 0, y is less than 1. We should say y has to be greater than 0, but less than or equal to 1, because the mass of it ends at 1. So this would be the range of that equation. Okay, so question C says, write the exponential decay model that relates the mass of Ra-225 remaining to time in 15-day intervals. Okay, so what we need is an equation. So we're looking for the half-life, right? Because it says it has a half-life in 15 days. Okay, so the mass according to time, so this is for question C, has a half-life. As time increases, we find out what the mass is. Okay, so that would be the equation to go with the picture. And it says estimate how many days it'll take for Ra-225 to decay to 1/30th of its original mass. So if we went 1 divided by 30, we would find that to be 0.0333 grams. Okay, so that's what we're looking for. So if we created a table and we had time and mass, and these points are already on the graph. So when the time was at 1, our mass was at 0.5. When our time was at 2, our mass was at 0.25. When our time was at 3, our mass was 0.125. Okay, and we can plug into the equation to find what it is for 4. So if we put 4 in for our time, I'm trying to move the page up here. Oh, maybe I can't. If we put 4 into our time, so we have this equation, and we're going to put 4 in. I'll just write my table here too. Okay, so if I went half to the power of 4, I get 0.0625. And if I put 5 in for the exponent spot, half to the exponent of 5 is 0.03125. Okay, so now we'll just kind of start trial and error, because the decimal we're looking for is 1/30th. So it is 0.0333, right? 5 is almost there, but it's too much, right? So it's got to be slightly less than 5. So what we can do is, in our equation, try something out that's just less than 5. So let's try 4.8. Okay, if we put 4.8 into that, we get 0.0359. So that's not quite there yet either. So let's try putting 4.9 in. If we put 4.9, we get 0.0335, which is pretty close to what we're looking for. So we could say that it's going to be 1/30th of its original mass after 4.9 15-day intervals. The assignment that we're going to do with that is 1 to 5 and 7, and that is on page 342.